we will be talking on functions or products of matrices that we do not really study in a regular linear algebra course. So exactly now my course, my talk will be more focused. So I hope the students who've done first course in linear algebra will be able to understand the talking fact. So
yeah, they have done
just
at
stick
least
to the
one
basics.
course.
Yeah, so it will be just first course of linear algebra that would be needed, and I'll stick to the basics and stick to the elementary things. So and something that is very simple, but you don't see in a regular linear algebra course at the same time. When we talk of products of between matrices, so one thing that we all know, that the first thing that we basically are introduced to is if I have, for example, let's just take two square matrices A and B, then the product AB, the ijth entry would be summation aik bkj. Now this is not, so if you look at the first time, it doesn't really look good. But now, on the other hand, if we look at the entry-wise product or the Hadamard product that we call, that's prevalent in literature, that is A not B, we will denote by. This is just nothing but the simplest idea that we can have, Aij, Bij. Just take entry-wise, ijth entry and multiply, and we get an n cross n matrix, and that is my Hadamard product. It's also called Schur product. Now, one will wonder that this is the simplest idea. This is the first thing that one will guess if we want to talk to just matrix product for layman. But why don't we talk about this? Rather, we talk about a more complicated object. Exactly, the reason being, now the linear algebra when we study, there we are studying not exactly just matrices, but we are also looking at matrices as linear operators. So if they're square on Cn or Cn to Cm, so they are linear operators. And the matrix multiplication, the standard matrix multiplication, corresponds to the composition of operators. So that basically connects us to the linear algebra, function analysis, operator theory. On the also in the same run, now if you change the basis, the matrix product basically adjusts itself. If I have changing the basis, basically in matrix terms, will give me a similarity transformation. XA X inverse, XB X inverse is nothing but XAB X inverse. On the other hand, now my Hadamard products are strictly dependent on entries. And therefore, they do not really behave well when if I change the basis. So they don't really behave well if I just strictly consider linear algebra as a thing. Also, a fundamental difference now that comes with the definition. If I have two rectangular matrices, if I want to take the standard matrix product, I'll have to talk of n cross k and k cross m kind of matrices. But here I'll have the Hadamard product of two matrices if and only if they have the same dimension. So two n cross k matrices I can have the Hadamard product. Now it's not that bad with algebra. So in fact, it's the simplest one. We all know that the space of matrices with scalar multiplication and addition forms a vector space. And when we take the matrix product, this is the matrix, this becomes an algebra. The similar thing happens with Hadamard products. It's an algebra. Now the fundamental difference being that Hadamard products are commutative. That makes them simpler even to think of than matrix products that are non-commutative. But then you will say that, okay, it doesn't go well with linear algebra and so on. So it doesn't, it's dependent, basis dependent, strictly based on dependent on entries. So why are we talking about that at all? Now, as Brother mentioned, so it pops up. So suddenly, so basically in many areas, so like in probability, statistics, computer science, and as well as not to mention matrix analysis. Special emphasis is there when we are talking about Hadamard product of positive semi-definite matrices. In fact, this is not a new area in matrix analysis or in mathematics. It has a long history and it has attracted attention of many big mathematicians. To start with, why do we call it Schur's product? Schur product. It's exactly because in 1911, more than a century back, Schur gave a fundamental theorem on Hadamard product, so it's a Schur product, and positive semi-definite matrices. So now, basically, let's just look at what is a positive semi-definite matrix. So if you don't, so just to recall, if I have, so an n cross n matrix, which is equal to its conjugate transpose, that is Aij is Aj bar, and x star Ax is greater than or equal to 0 for every vector x in Cn. It's positive semi-definite, and it is positive definite if x star Ax is greater than 0 for every non-zero x. Equivalently, every positive semi-definite matrix is positive definite if and only if it is invertible. You also would be knowing that every positive semi-definite matrix has all eigenvalues non-negative. Every positive definite matrix has all eigenvalues strictly positive, and so on. A simple result that we'll be looking at. So just as a reminder that if A is positive semi-definite, if and only if x star Ax is positive semi-definite for any x n cross n matrix x. Okay. Now, before going to the Hadamard product, just for the contrast, let us see how do the matrix products behave with the positive semi-definite matrices. Now, if I take A and B to be positive semi-definite matrices, their usual standard matrix product AB is positive semi-definite if and only if I have the most stringent condition that I can think of when I'm talking of matrix theory is AB is equal to BA. The two matrices commute. So it's exactly under no non-trivial condition, so as to say, my AB would be positive semi-definite. Though the situation is not that bad, the eigenvalues of AB, though AB need not be positive semi-definite, but eigenvalues of AB are always non-negative, and as a consequence, trace of AB will always be non-negative. But now, when we talk about Hadamard products and the positive semi-definite matrices, we have a best time that we can think of. If I have two positive semi-definite matrices, their Hadamard product is again positive semi-definite, and that goes back to Schur in 1911. So he studied these products in context of positive semi-definite matrices extensively, and that's why, so there you'll see that we call them also as Schur products. So now he gave also an upper bound and lower bound for the maximum and the minimum eigenvalues of the Hadamard products in terms of the diagonal entries and the eigenvalues of the two matrices. Also, now remarkable is the fact, if I want to have A not B to be positive definite, I really don't want that A and B to be both positive definite. That would be the natural thing that one will guess. But even under the weaker condition, that A is, so one of the matrices is positive definite, the other has all positive, strictly positive diagonal, then I have the Hadamard product of the two matrices to be positive definite. So exactly now, see how strongly my Hadamard product behave with positive matrices. Also, one very important result when we come to application is if I have A to be positive semi-definite, C to be any matrix, then we can find the norm of A not C. but we will be focusing on coming back to this result after again in this lecture. But let's see that now where were the first occurrences of these products. Now, surprisingly, these were not in linear algebra, not in matrix theory, not in analysis, but in the study of partial differential equations. And that too before Schur. Way back in 1894, Mautard basically used these products. So these products occurred for the first time in Mautard's theorem to prove the uniqueness of the boundary value problem for linear elliptic partial differential equations. So if we have the partial differential operator LU, so U is in D, which is a subset of Rn, and we have it on the domain. So LU we take is the operator summation over ij, aij of x del square u by del xi del xj plus summation bix del u by del xi minus cxu. This is called elliptic if I make the matrix AX as with the ijth entry aijx, that is a positive definite matrix for every x in D. So now we are up with the matrices. How do the Hadamard products come into picture? Let's see. So if we take AX as aijx, bx as the vector bix, now the gradient, so you would have done a course in several variable calculus. So dux, we denote as the gradient at x, so del u by del xi at x. And hux to be the n cross n matrix, which is the Hessian. So that is del square u by del xi del xj. So now what is summation over ij, aijx, del square u by del xi del xj? This is nothing but the sum of all the entries of the matrix, that is AX, Hadamard product with HUX. And that also we can write in terms of the inner product. So E transpose AX, not HUX, E, where E is the vector of all ones. So if you compute, it's a very simple calculation. So this is this E transpose AX, not HUX, E. And remember, when we are talking of elliptic equations, AX is positive. And we also have that we can, when we are talking of Hadamard products, we can multiply any two matrices provided they have the same dimension. So in that case, we can multiply even two vectors. So my summation bix u by del xi is nothing but the sum of all the entries of the Hadamard product of the vectors bx, not dux. Okay. Now we will come to what Mautard did. So now obviously Mautard didn't have Schur's theorem. He employed a little it's a more complicated arguments. But we have Schur's theorem in our rescue, so we'll be using Schur's theorem. Nevertheless, it's interesting to see how easy and how if elegant the whole thing looks like when we use Hadamard products and Schur's theorem. So now let us assume that Cx is strictly greater than 0. We consider the boundary value problem, Lu is equal to 0, with the boundary condition that u is equal to 0 on boundary of D. Let's start with that. Now let u be a solution of this problem and take x to be a local point of local minimum. Now that gives me that the gradient dux at this x will be 0 and hux will be a positive semidefinite matrix. Now, Schur's theorem tells me that AX not HUX is positive semi-definite, and that gives me that E transpose AX not HUX, E is greater than equal to 0. And that tells me that the first term in the differential partial PDE that we had is positive. The second term, because dux is 0, is 0. And the third term, Cx is greater than 0. So that can be, the whole equation can be 0 if and only if my u is greater than equal to 0. So if x is a point of local minimum, ux is greater than equal to 0. Now, if x is a point of local maximum, in that case, my minus HUX will be positive semi-definite, and the whole inequality will reverse. So my UX will be less than equal to 0. And where I know that U is 0 on boundary of D, when is that possible? It's possible only when U is identically 0. Now, so I'm not going into details, but using simple analytic arguments, one can extend the whole thing to Cx being greater than equal to 0. So what was the result proved by Mautard? This is the uniqueness theorem that we have. So if we take the boundary value problem for the real linear elliptic partial differential equation, Lu is equal to 0 with the boundary condition that U is equal to F on boundary of D. So now that will have a unique solution. So if U and V are two solutions of this boundary value problem, U minus V is the solution of Lu is equal to 0 with boundary condition that the solution is 0 only. And basically the previous discussion applies. And now this will also give us Laplace equation that we'll be aware of. So del square u by del x squared plus del square u by del y squared is equal to 0. So that is, okay, that's in the category of elliptic PDEs. My AX is nothing but the identity matrix, and it gives us the uniqueness of the solution for the boundary value problem for Laplace equation as well. There are many other occurrences. I'll point out one more just in this talk, and that brings up so a little of matrix analysis and applications in other areas. So let us look at go back to the first course in linear algebra. You would have done spectral theorem. So if A is a Hermitian or self-adjoint matrix, then you can diagonalize it by a unitary matrix. That is, there is a unitary matrix U such that E is equal to U star DU. Where what is D? D is the diagonal matrix, and the diagonal entries of D are the eigenvalues of A. A is Hermitian, eigenvalues all will be real. Now if I take, so I'm just focusing on my talk. So basically we can do much better. We need not really consider continuously differentiable functions. We can go with continuous functions. We need not just consider f from R to R. We can go to f from I to R or so on. But let's just stick to f R to R and see one. That will give us a very good idea of the whole thing. So f is a real valued function on R, which is continuously differentiable. I know that if f of lambda 1, f of lambda 2, f of lambda n will be well defined. So what will be fd if I want to define? That will be diagonal matrix f lambda 1, f lambda 2, f lambda n. And this is called a standard functional calculus. So I define the standard function of A, so f of A, to be u star fdu. So this is the standard function of A. We'll come to Hadamard functions of A in a few minutes. So this is generally when we talk of functions of matrices. These are one kind of functions that we talk of more often. So now see, if you would have tried to find derivatives of functions from Rn to Rn or so, and in fact, now that is not a very easy task all the time. To make sense of the derivative is even difficult, more difficult. And if I'm talking of function from matrix to matrices, the space of matrices to matrices, so now it's basically Mn or Hn is like Rn squared. So going via the partial derivatives and all those things will make the things very, very intricate and not look good. So now one can talk of, so these are not very simple problems always to find the partial derivatives of functions of matrices. But there is a very interesting result, a formula called Delaski-Crane formula that gives us the derivatives of at least the functions that we lift from R or in intervals. Again, we can do better than that, but just this is a sample result. So two space of matrices, and the simple formula is in terms of the Hadamard product of two matrices. So dFA at B is equal to the Hadamard product of F lambda I minus F lambda J by lambda I minus lambda J and B. Now see, this is, we calculate in the orthonormal basis when A is diagonal. So that means we are talking of U star du, so we are changing the basis. But if you just spend 2 minutes or so, you'll see that that doesn't really, so it just so it doesn't really affect anything, because in the expression, so as to say, it just will introduce some congruences by U, nothing more than that. So we have a formula for the derivative of F at A. The matrix that appears, F lambda I minus F lambda J by lambda I minus lambda J, these are called loner matrices with respect to F, and they have their own independent importance. So basically now see, as soon as we have Hadamard products coming into picture, we have Schur's product theorem, Schur's theorem, those 4 points, we can find the norm of the derivatives, we can make sense of. So these, again, not just in matrix theory, these are very important. This turns out to be a very important result when we are talking of operator monotone functions, the relationship between the loner matrices, the special functions, operator convex functions, and also, not to mention, so a very important area is perturbation theory. And because this allows us, this formula as well as Schur's theorem in combination allows us to calculate the derivative of the norms. And that in turn are very useful in perturbation theory. So these were just two occurrences of the Hadamard products. Let us go back to our Schur's theorem. Just to recall that if A and B are positive semi-definite, A not B is positive semi-definite. If one of the matrices is positive definite, the diagonal of the other is strictly positive, then the Hadamard product is positive definite. There are many proofs at present to this result. And one of the most standard proof that we basically just say, that's a one-line proof. Now, who know tensor products will understand. So, the Hadamard product of A and B, A not B, is a principal submatrix of A tensor B. If A and B are positive semi-definite, it's very easy to see that A tensor B is positive semi-definite, and therefore, my principal submatrix would be positive semi-definite, and so on. But we will look at a very, very elementary proof that doesn't require more than just what I have mentioned in this talk. the definition of positive semi-definite matrices, and some of the very basic properties. So let's start with the proof. It's just a 2-3 line proof, and so it's a nice thing to just have such an elementary proof to such a fundamental theorem, such an important theorem. So we are taking two matrices A and B, A not B. So what we are interested in is, if you remember, so if A and B are positive semi-definite, for example, then Aij will be Aj bar, Bij will be Bj bar, A not B will be obviously self-adjoint or Hermitian, whatever you say. So we are interested in looking at X star A not B X, where X is a vector, small x. Now what we do is we consider capital X to be the diagonal matrix x1, x2, xn. Okay. Now what we are looking at is X star A not B X. That will be summation over Ij, X per I, Aij, Bij, Xj. We write this as, now you see, X per I, Aij, Xj, Bij. Now, if you look this just for a second, so X bar I, Aij, Xj, that is the ijth entry of X star Ax, where X is the diagonal matrix x1, x2, xn. So therefore, now this turns out to be the trace of X star Ax, now Bji bar, so that will be B bar. But if B is positive, my B bar is positive semi-definite as well. And we know that, so X star Ax, because A is positive semi-definite, X star Ax is so, B bar is positive semi-definite. We know that if there are two matrices C and D, so that they are positive semi-definite, trace CD is greater than or equal to 0. And therefore, my trace is greater than or equal to 0, and that we wanted for positive semi-definiteness. Now, a little 2-line work that will be a good exercise for the students to show that if B is positive definite, A has all diagonal entries strictly positive, then in that case, my trace X star Ax, B bar will be strictly greater than 0 when X is non-zero. So if X has at least one non-zero Xi. So that gives us the positive definiteness also in the under the additional conditions. Now we turn to, so we were working on Hadamard products that require two matrices. We turn to the function of single matrix. An immediate consequence of Schur's theorem. So now if I just start with a single positive semi-definite matrix A not A will be positive semi-definite. A not A will be positive semi-definite. And therefore, if you keep on doing that, so if we now introduce the term the mth Hadamard power of this matrix. So Aij power m. If A is positive semi-definite, Aij power m will be positive semi-definite. That raises the question, now this is a particular function of a matrix that is applied entry-wise to the matrix. So let us consider a more general case. F is from S to R and A is Aij, where Aij belongs to S. So in that case, I can define the Hadamard function of A. So F, to distinguish, it's a square brackets A to be the matrix with ijth entry F of Aij. Now here, so let us look at, so what will be the matrices? One of the functions. So now, because of applications, mainly probability and statistics, and so we are interested, one becomes interested in what are the functions that preserve positivity. So immediately we have one example, that is the mth Hadamard power of A. So that is the p power m, where m is a non-negative integer that preserves positivity when applied entry-wise. Now we know that the sum of two positive semi-definite matrices is again positive semi-definite. Non-negative multiple of a positive semi-definite matrix is positive semi-definite. Therefore, if I take a polynomial, summation alpha I x power I, where alpha is greater than equal to 0, then I will have that my polynomial function applied entry-wise, that is the Hadamard polynomial, summation alpha I in power mod I, is positive semi-definite. Now one can also see easily, if I take a limit, the limit of sequence of positive semi-definite matrices, this is again positive semi-definite. And therefore, now, so basically, you would have seen power series. So what is power series? So it's the limit of the polynomial summation alpha I x power I from 0 to n. Taking convergence well into account. So if I have a power series with non-negative coefficients, and which is so convergent when x is equal to non a, so it will converge for p. So summation alpha I aij power summation alpha m aij power m. So in that case, that is again a preserves positivity. So that gives us that if I start with a positive semi-definite matrix A, e power aij will be positive semi-definite, 1 by 1 minus aij will be positive semi-definite. And these are important in studying kernels, studying in statistics, and so on. So one can look at Professor Baput's book. There's a non-negative matrices and its applications. So, okay. But now the interesting thing is we have a class of functions that preserve positivity. Remember, I have not talked of the dimension of matrix. It's independent of the dimension of matrix. Only thing that I require when I am talking of polynomials or power series is that they should converge. Now, there is nothing to talk about dimension here. So now the interesting question, in fact, that has basically attracted many big mathematicians for a long time, is that what is the precise class of functions that preserve positivity? And the precise class of functions that preserve positivity, in fact, so again, I'm giving you a sample result. So we can, so proved by Schoenberg way back in 1942, then done something by Rudin in 1959. There have been many more versions, many variants. So if f is a function from -1, 1, so we can change the domain. There are variants which changes the domain. But let's stick to this sample. But basically the idea is the same. So the result, if we say without trigger, it's the same. So what will be the thing? F is from -1, 1 to R. That preserves positivity. So f squared brackets a, the Hadamard function f at a, is positive semi-definite for all n cross n positive semi-definite matrices and for all dimensions n, if and only if f is analytic and its Taylor series expansion. So that's why it's at 0 is in the domain. So its Taylor series expansion has all coefficients non-negative. So it's something, so most of the times in general, it's very hard to get necessary and sufficient condition for something. It gives us a necessary and sufficient condition, if and only if condition. But now see, what is this class? This is a small class. As compared to continuous functions or even infinitely differentiable functions, analytic functions makes a smaller class. And in that also, we are having the restriction that all coefficients should be non-negative. So then now, So what basically, so it's the, now that becomes very restrictive when we want to apply, when we want to look at functions that preserve positivity. And many a times in applications, what happens is that we are not working with all dimensions of matrices. So typically, where will we need statistics or we'll need in computer science? So there we are working with matrices which have the dimensions have an upper bound. So now in that case, it suffices if we have a characterization of functions that preserve positivity for fixed dimensions. And that, in fact, turns out to be a very hard problem. There are conditions, there are necessary conditions, there are sufficient conditions, but there are not necessary and sufficient conditions till date. And people are interested, there are results. Time to time, there are studies restricting the rank, restricting the structure of the matrix, restricting the, restricting the function itself, that what kind of functions, studying specific functions, and so on. So exactly, now we'll turn to one specific function that proves out to be quite important when we are talking of probability and statistics. It was first studied in context of Weber conjecture, and also, so basically to regularize data, it's important. In study of movement sequences, it's used. So recently, there have been a lot of interest by Prof and his co-authors. And so, and related to, so a lot of group representation comes in there, and a nice matrix analysis, and a combination of many areas. So here, we have talked about the non-negative integers, but we talk about the real powers. So let us change non-negative integers to R, where R is greater than or equal to 0, is a non-negative real power. So Aij power R, we are looking at the matrix now. Obviously for that, we need Aij's to be all non-negative. So we have the term doubly non-negative matrix, that is a matrix which is positive semi-definite as well as the entries are non-negative. Now we see that this is not as good as my non-negative integer power. Even with the square root, so a power not 1 by 2, it doesn't preserve positivity even for a 3 cross 3 matrix. So that basically motivates us to introduce a smaller category of matrices, so infinitely divisible matrices, that Aij power R are greater than or equal to 0 for all R greater than or equal to 0. So Aij power R is positive semi-definite. Then when we start with an Aij is a double non-negative matrix. One can easily see that 2 cross 2 matrix is positive semi-definite. Infinitely divisible. So A11 is greater than or equal to 0, A12, A12 square is less than or equal to A11, A22. That will give me that for the power R also. Also, if I work with the rank 1 matrix, positive doubly non-negative matrix, it's again infinitely divisible, because I can write the rank 1 positive doubly non-negative matrix as xi xj, and then therefore xi power r, xj power r will be again doubly non-negative. But clearly, now what happens when a power not r is, so we have seen that it's not true for all. So if we go beyond dimension 2, or we go beyond rank 2, rank 1, we are in a trouble. Way back again in 1977, FitzGerald-Horn, it's their classical result. They actually characterize the powers that preserve positivity. For now, we're having the dimension fixed as n. So my a power not r will be positive semi-definite if and only if r is greater than or equal to n minus 2 or r is a non-negative integer. R is a non-negative integer, comes by Schur's theorem. R greater than or equal to n minus 2. Now, if somebody is interested, you can look at their proof. And that, so the most beautiful thing about the whole thing is, the whole topic what we're talking of, it uses analysis, basic analysis, but in a clever way. So Aij power R, so now what does it say? If I have R greater than n minus 2 or R is an integer, and I pick up any n cross n positive doubly non-negative matrix, A power not R will be positive semi-definite. But if R is not an integer or R is less than n minus 2, in that case, this would not be so. So that means that what that showed, that there is a small enough epsilon such that 1 plus epsilon ij whole power R will be not positive semi-definite. Now that was a specific example based on existence, small enough epsilon. So what is the significance of epsilon ij and so on? So it's that's for a specific matrix, it's anything special. Now it turns out that it is not so. In fact, we're coming to the end. So we can replace epsilon ij by any xi's as far as the xi's are distinct, and 1 plus xi xg is strictly greater than 0. So 1 plus xi xg power r would be positive semi-definite if and only if r is greater than or equal to n minus 2 or r is an integer. That means now it's not the existence of the matrix, it's for all matrices this will happen, the matrices of this form, 1 plus xi xj. In fact, this allows us, so now in the proof, while doing the proof was quite indirect, but there we have a lot of interesting remarks. So I'll just conclude with certain remarks. Now these results, when we look at the proof, they just not talk about the positivity, that when it will be positive, when it will not positive. The strength of the result is that they give exactly the number of eigenvalues that will be positive, negative, or 0. The most interesting thing is, I have started with a talk that Hadamard products or Hadamard functions, or these are dependent on entries. Now the behavior of the Hadamard, the positivity, the number of eigenvalues being positive, negative, 0, these are not dependent on entries, but only dependent on the dimension n and the power r. Also, these basically give us nice results on ranks. But now, so we can actually fully characterize rank 2 matrices. We have studied rank 2 matrices with positive entries, not with non-negative entries. But rank 3 matrices are still mystery to us. Similarly, even the rank questions are not solved for rank 3 matrices. And there are related problems on monotonicity and convexity preserving Hadamard functions. So that opens up again a new topic altogether related. So there have been many results, and again, the questions are very simple to pose. The whole thing looks very simple, but the solutions are not that simple always. And we don't have solutions to many problems here, in fact. So that's, I end the talk with this. These are the references. So these are one of the things, including the excellent survey by Horn. So, and some recent papers that talk about these topics. There are more papers by Apurva and their co-authors, the 9th. So that shows that how applicable and just not sticking to matrix analysis, how representation theory and all those things come into picture when we are talking of. So it looks really like just a matrix analysis problem, but we go quite far. Thank you.
Okay, thank you, Tanvi, for your nice talk. I just want to add one thing here, that the problem seems to be quite a cooked up problem, but at the same time, it turns out that it comes everywhere. For instance, in statistics, probability, and many things naturally in information theory, and probably in the other areas which I am not very familiar with. Okay, so questions. Yeah, so if no other question, then maybe we can just thank our speaker.